Hello everybody, and welcome back to another Big Ideas lesson for Algebra 2. Today we're talking about section 7.4, which is adding and subtracting rational functions. Now, last time we learned how to multiply and divide them, and we learned that the rules for multiplying and dividing fractions also works for multiplying and dividing rational expressions. The same deal happens here. If we know how to add and subtract fractions, we'll know how to add and subtract these rational expressions. So here, I've included a little bit of a warm-up for you to try out. I want you to try all three of these problems and see if you can remember how to add and subtract fractions. I'll give you a hint. You might need to get the denominators to look the same. Pause the video and try them out. Hopefully you've had a chance to pause the video and try these out for yourself. If not, let's go through. Anytime you add or subtract fractions, the denominators must match. They have to have a common denominator. If they don't, you can't do it. So here the denominators are both 5. My recommendation is this. To add or subtract fractions with common denominators, down here, treat the denominator almost like a unit, something that won't change. Like 3/5 plus 12/5 is how many fifths? That's a good way of putting a question like that. The denominator is going to stay the same. So we treat it like we have 3 of them plus 12 of them. That's 15 of them. Only thing we need to do now is see if it simplifies, and it does. 15 over 5, if I can divide the top by 5 and the bottom by 5, I just get 3 over 1, or 3. The next one's a little trickier, though, because the denominators aren't the same. So what can we do? We have to remember the rule of equivalent fractions. To turn one fraction into an equivalent fraction, like here we can all agree that 1/2 and 2/4 are equivalent fractions, you have to multiply the top and bottom by the same amount. If I multiply 1 times 2, you get 2. If I multiply 2 times 2, you get 4. So that's an equivalent fraction. We need to turn 1/4 into an equivalent fraction that's over 8, though. So we ask ourselves, what do I need to multiply the top and bottom of my fraction by to make my denominator 8? In this case, to turn a 4 into 8, you've got to multiply by 2. So we also multiply the top by 2. 2/8 minus 3/8 is what we're left with. 2 minus 3 is -1. So your answer is -1/8. Last but not least, what if we have 2 different denominators where it doesn't look like they can multiply to make each other? Like, there's nothing I can multiply 4 by, or at least not a whole number, that would give us 7. So what can we do? Well, we need to turn them into an equivalent fraction, or into equivalent fractions, I should say, where they both have the same denominator. So we both want them to be over the same number. The question is, what number? To answer that, we should find the least common divisor, the least common multiple of these two numbers, the LCM. What is the lowest number that 7 and 14 are factors of? The answer is 28. Think about it. 7 times 4 is 28, so both 7 and 4 are factors of 28. Now we just got to figure out what to multiply the top and bottom by to make 28. Well, in this left fraction, we want to turn 7 into 28, so we should multiply by 4. 4 times 7 is 28, and 4 times 2 is 8. On the other one, we have a 4 on the bottom that we're trying to make into 28. 4 times 7 is 28, so 5 times 7 should be on top, or 35. Our final answer here is 43 28ths. Done. Overall, if you cannot think of something that the two bottom numbers multiply to make, multiply them by each other. This is a guideline that's going to help us out a lot in this section. So the rule, as you could probably expect, is the exact same if we have rational expressions. If we have common denominators, it's a lot easier. Like, notice that in example 1a, we have a common denominator. As long as you have a common denominator, you can just add or subtract the numerators. Like 12 minus 2, isn't that just 10? So you could write this as 10 over 5x. The only trick is now we have to ask, can it be simplified? Because usually with these problems we can simplify something. In this case, 10 divided by 5 does simplify. They're both divisible by 5. 10 divided by 5 is 2. 5 divided by 5 cancels out. Our answer is 2 over x. What about question B? Well, here in question B, same thing. We have a common denominator. The only difference is 3x plus 1 and 2x plus 5 don't simplify. They don't. There's nothing we can cross off here. So this is just our answer. Now, with question C, my advice is this. See if anything in the problem can be simplified first. Then go through and simplify when you're done. So first off, can anything be simplified right away? Not really. So let's just go and write out x squared minus x. But remember, it's not just minus the x, it's also minus the 2. So it's negative 2. Just like when we were subtracting polynomials last unit, if you're subtracting a whole polynomial, you should distribute the negative and make sure you're subtracting every piece of it. We're not done though. We should check to see if this can be simplified further, and it can. If I set up a combinator for this one, because again, it's a trinomial on top, the last number is negative 2, the middle number is negative 1, what two numbers multiply to make negative 2 and add to make negative 1? It's going to be negative 2 and positive 1. So we can just write our top as x minus 2 times x plus 1, and that's all over what was originally down there, x minus 2. Oh, now I see a cancellation. There's an x minus 2 on top and an x minus 2 on the bottom, so we cross them off. The only thing that we're left with is x plus 1. We are not done yet, though, because remember, anytime you get rid of a factor that has an x in it that was in the original problem, but not in our answer, we have to restrict our domain. It's x plus 1, with the exception that x cannot equal 2, because 2 minus 2 is 0. The rule is this. Look at your answer. Look at all your steps. If there's a denominator that was in your steps but is not in your final answer, check to see if there's a restriction. So here, we don't see an x minus 2, but over here we do. That means you have to restrict x minus 2. X can't be 2. All right. What if we had different denominators, though? Like, let me just make up a weird, crazy problem. Let's say I had 4 over x times x plus 1 plus, I don't know, 10 over x. Sure. Well, here, we've got something a little bit interesting. We can't add these unless they have the same denominator. So what can we do? Well, I've put it in 3 steps here. First step, factor the denominators of both expressions. It's already factored, so we don't need to do that here. Then, multiply either one expression or both of them by whatever they're missing to make a common denominator. So here, if we take a look, this one has an x times x plus 1. Here we have just an x. So it's missing an x plus 1. Multiply this expression by what it's missing. It's missing an x plus 1, so let's multiply. As we multiply that out, we get the following. We get 4 over x times x plus 1 plus 10 times x plus 1 over x times x plus 1. Beautiful. And now that they have a common denominator, we can add them. As we go through and add, one thing that I would highly, 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 highly recommend, in fact, it's basically required, is that if these things don't combine, try to do what you can to make them combine. Like, normally we would just write out our answer as 10 times x plus 1 plus 4. And our denominator would just be x times x plus 1. But we always want to check if something cancels. And right now, nothing cancels. What we need to do is we need to multiply out this 10, see what we get, then factor the whole thing once again. As a reminder about why this doesn't cancel, both the 10 times x plus 1 and the 4 are over x plus 1. You can only cancel stuff if the numerator is all being multiplied. So let's go through and simplify it. We have to distribute our 10 to the x and the 1, giving us 10x plus 10 plus 4 on top, and our x times x plus 1 on the bottom. 10 plus 4 can be combined, so we should absolutely do it. We get 10x plus 14 over x times x plus 1. And now we see that this can be, once again, all factored. 10x and 14 both have a 2 in common. So write it as 2 times x plus 7 over x times x plus 1. This is now totally factored because there's no more addition or subtraction. If there was an x plus 7 on the bottom, we might even have a cancellation. But in this problem, this is just the final answer. Be very careful, because with these problems, you're not done until your addition or subtraction is pretty much all gone. All you have is factors. Let's flip to the next page and take a look at example 2. Example 2a we're going to do together. I want you to try examples B and C on your own. So let's do example A. Right here for example A, we are told that x over x plus 2 plus 4 over x plus 5 is what we're trying to simplify. But they don't have the same denominator. Here we have an x plus 2, here we have an x plus 5. So what can we do to make them look the same? Unlike the problem we did together, we can't just multiply one of them by something and boom, they're identical. Here, we need to multiply both of them to make them look the same. We ask, what's missing from the first one? Well, in the first one, we're missing an x plus 5. So we should multiply by x plus 5 on the bottom and on the top. Okay, what are we missing in the second one? Well, in the second one, we're missing an x plus 2. So let's multiply by x plus 2 over here. And let's also multiply by x plus 2 right over here. When all is said and done, we end up with x times x plus 5 over x plus 5 times x plus 2 plus 4 times x plus 2 over x plus 5 times x plus 2. We're going to want to add these together. However, we also want to distribute these. It'll make it a lot easier to add. So we're going to distribute the x's and we're going to distribute the 4's. What we end up getting is x squared plus 5x plus 4x plus 8 all over x plus 5, x plus 2. Forgot a parenthesis. Okay, well, after we combine, whoops, I realize you guys can't see that. After we combine 5x and 4x, we're going to end up with like x squared plus 9x plus 8. Can this be factored? Let's look to see if there's two numbers that multiply to make 8 and add to make 9, and there is. The two numbers that multiply to make 8 but add to make 9 are 8 and 1. 8 times 1 is 8, 8 plus 1 is 9. So we can rewrite the top of our fraction as x plus 8, x plus 1, all over what we had before, x plus 5, x plus 2. As we look, nothing really cancels out, so this is our final answer. It's in factored form. No more addition or subtraction outside of parentheses. I'd like you to pause the video and try these next two out on your own. I will once again give you a hint that if you want to solve these, you're going to have to factor your denominators first to see what you need. Pause the video and try them out. How'd you do? The first one, B, is a little bit easier. There's not really any simplification you need to do afterwards. But C, I feel like I should elaborate on just a little bit. In case you want to see the steps for both of them, I've got it all on this page here, so you can pause the video to look through the steps for B and C, but I want to focus on the ending of C here. For part C, we did all the steps we normally do. We cancel out the x squareds plus 1's and divided 6 by 3 to get 2. However, where did this I come from? I don't see anything that would have to do with I in this problem. Well, remember, with our restrictions, anytime we cross off something in the denominator, we want to figure out what would make that factor 0. To find out what makes a factor 0, we should set that factor equal to 0 and solve. So if x squared plus 1 equals 0, we would have to subtract 1 from both sides, giving us x squared equals negative 1. To find out what x should be, we should square root both of these. The square root of x squared gets us our x by itself. But on the other side, we get plus or minus the square root of negative 1. And we know that by definition, the square root of negative 1 is just I. Oops, I realized I forgot the plus or minus there. So x can't be I, and x also can't equal negative I. Last but not least, we're talking about adding and subtracting rational expressions with something called complex fractions. Oh boy. This is where we put together dividing fractions and adding and subtracting fractions. We're not going to learn any new things other than what a complex fraction is. But I am going to show you two methods of tackling them. So, a complex fraction is a type of fraction that has more fractions in its numerator or its denominator. So like in lesson 7.3, if I gave you 3/5 divided by 4/7, this would be a complex fraction. The most important thing to consider is this. Across this bar here, we still have a numerator and a denominator. This is our numerator, and down below is our denominator. But each of those have a smaller numerator and denominator. So like here, this is our numerator, this is our denominator. On this one down here, we've got another numerator and another denominator. On this one here, we've got another numerator and a denominator. It's a lot to handle. But just know that when I say do this to your numerator, I usually mean the big numerator. Otherwise, I'll tell you what I'm talking about more specifically. So, these look horrifying, but there are a couple of options to make it easier. The first method I'm going to teach you is something I call the step-by-step method. And it involves just doing what we've always done with addition, subtraction, multiplication, and division problems. The first step to this is recognizing that, hey, this denominator has an addition sign in it. If we could add these two together, it might not be super simplified, but it'll at least be a little more simplified. Your first step is to simplify your numerator and denominator until you have just two fractions being divided. So let's do it. To simplify this, we're looking to add together 1 over x plus 4 plus 2 over x. In order to do that, we need to ask ourselves, okay, how can we get these two denominators, the x plus 4, which I'm going to write in red, just so we can keep track of what denominator we're talking about. How do we make our red denominator and our green denominator the same? Well, we know that we should multiply them by each other. This term is missing an x, so I'm going to multiply the top and bottom by x. And this term is missing an x plus 4, so I'm going to multiply the top and bottom by x plus 4. What this results in is our denominator becomes x over, I'm going to write this out in the right colors, x times x plus 4, 2 times x plus 4 we can kind of do in our head, because we know that 2 times x is 2x, 2 times 4 is 8, so it's 2x plus 8 over that same denominator, x times x plus 4. And now we can just add and simplify like normal. When we add these together, first of all, our numerator stays the same. We didn't do anything with our numerator just yet. X plus 2x is 3x. So this is 3x plus 8 over x times x plus 4. Nothing else can be simplified here. 3x plus 8 can't be factored. This is already factored. So we've done the first step. We've added the denominator. Now we can divide these two big fractions. We can divide the fraction up top by the fraction on the bottom. Whenever you're dividing two fractions, remember what we do? We keep, change, flip. So let's keep 5 over x plus 4 the exact way that it is. We're going to change our division sign into multiplication, and we are going to flip our denominator, the big denominator right here, to be x times x plus 4 over 3x plus 8. And when we multiply, just like we did last section, we ask, what can be simplified? There's only one thing that can be simplified here, folks, and that's the x plus 4s. So we cross them off, and our final answer is 5x over 3x plus 8. Done. Whew. A little bit of a lengthy process here, a little lengthier than the other problems. But overall, it's just using the skills that we already know. It's like if I was to give you a really long problem where it's like 3 plus 2 divided by 5 to the power of 3 times 2. It's just more. It's not harder, it's just more. If you know each of your steps, then you can believe in yourself with full confidence that you will get through it. Method number 2 is a little bit quicker, but also a little bit different. So let me write down the problem again. Here we have 5 over x plus 4 divided by 1 over x plus 4 plus 2 over x. Method number 2 is find a greatest common factor that works for all denominators. Look at all the denominators in our problem. We have an x plus 4 here, which again I'm going to color in blue. We have an x plus 4 down here, which I'm going to color in red. And we have an x. So what could we multiply each of these individual fractions by to make those denominators match? Well, just like before, the x plus 4 terms are missing an x. So we can multiply those fractions by x. And the 2 over x is missing an x plus 4. So if we were able to put all of these together, what would we end up with? We end up with 5x over x times x plus 4 divided by x over x plus 4 plus 2x plus 8 over x plus 4. Whew, boy, what a mess. But you may notice that this looks exactly like the previous step up here, all in one go. That means it's going to be easier for us to simplify. We just have to repeat the same steps as before. Now, I'm going to teach you a little bit of a shortcut here as well. First off, we know that these are going to add together to make 5x over x plus 4 over 3x plus 8 over x times x plus 4. The shortcut I'd like to teach you is this. We know that when we flip these fractions, there's going to be an x times x plus 4 in the numerator and x times x plus 4 in the denominator. So they're going to cancel out. The shortcut is this then. The shortcut is if you have two fractions dividing each other with the same denominator, you can just straight up cancel out those denominators. There we go. So, with canceling these out now, we can just write our answer as 5x over 3x plus 8. Something I totally forgot to do with these problems is write down the restrictions. But we can kind of see what happened. In our original denominators, well, maybe not original, but at some point in the process, we had x times x plus 4s in the denominator. The x and x plus 4 both disappeared. There's no x or x plus 4 factors in the denominator in our final answer. So we say that x cannot equal negative 4 and x cannot equal 0. If x was negative 4, at some point in this problem, we would have our dividing by zeros and break the problem. And if at some point x was 0, this would be 0 times x plus 4, breaking the whole problem again. Of course, the restrictions are going to be the same here, but it's a little easier to see in this version because we can actually see that we canceled out the x and x plus 4s. It's a little harder to see up here. All right. Last but not least, we have one last problem. I'd like you to try this one out on your own using your method of choice. I'm going to put both methods up here in a moment in case you want to see the walkthrough, but I'd like you to pause the video one last time. Try these out. All right, let's do it, y'all. We're going to start with the step-by-step method. So, in the step-by-step method, where we have 3 over x plus 5, all divided by 2 over x minus 3, plus 1 over x plus 5, we ask ourselves, how do we simplify the denominator first? Well, in our denominator, we have an x minus 3 denominator and an x plus 5. So we need these to be in common before we can add them together. To make them in common, we should multiply them by each other. So this fraction should be multiplied by x plus 5, and this fraction should be multiplied by x minus 3. What we end up getting is 2 times x plus 5 is, let me write out my numerator first, totally forgot that for a moment. 2 times x plus 5 we can just write as 2x plus 10. Our denominator is going to be x plus 5 times x minus 3. Over here, 1 times x minus 3 is just x minus 3. And that's going to be divided by x plus 5 times x minus 3. When we do 2x plus x and 10 plus negative 3, we get the following the following simplified fraction. We get 3x plus 7 over x plus 5 times x minus 3. Now, since we just have one fraction divided by one other fraction, no adding or subtracting of fractions here, we can do our keep, change, flip. We keep 3 over x plus 5. We change our division into multiplication, and we flip our big denominator so that its littler denominator is on top and its littler numerator is on bottom. Here, when we multiply things out, we can go through and actually do this multiplication. It's going to be a little bit trickier to do, however. We do see some things cancel out, thankfully, but there's going to be something tough here. We see that the x plus 5s will cancel, saving us from a lifetime of hurt. We have 3 times x minus 3 over 3x plus 7. The tough part is to figure out our restrictions. Well, look at all the denominators we had in the problem before. What are we missing now? We're missing an x plus 5 and we're missing an x minus 3. So the restrictions, which is the toughest part here, are negative 5 and positive 3. Because if at any point in the problem x was negative 5 or 3, the denominators would turn into zeros and ruin everything. Let's do the same thing with the GCF method. As a reminder, the GCF method asks, instead of us looking at each problem piece, look at the whole problem and ask, how can we turn all those denominators into the same thing? Well, we have some x plus 5s, but we also have an x minus 3. So the x plus 5s are missing an x minus 3. I'm going to multiply this fraction by x minus 3. And this one down here should also get multiplied by x minus 3, since that's what they're missing. But this one has an x minus 3. It's missing an x plus 5. So we multiply x plus 5 times these two. Now we've got a little bit of multiplying to do. We can write out our, not really simplified, but our slightly more simplified version as 3 times x minus 3 over x minus 3 times x plus 5 all over 2 times x plus 5, as we mentioned, is going to be 2x plus 10. 1 times x is x. 1 times negative 3 is negative 3. So what's 2x plus x but 3x? And what's 10 plus negative 3 but 7? Remember our trick? The trick is, if the denominator of the top and the denominator of the bottom are the same, cancel those denominators out, and what's left over will be your fraction. So what's left over is 3 times x minus 3 on top, and 3x plus 7 on the bottom. And once again, since we canceled out an x minus 3 and an x plus 5, it's much easier to see now that our restrictions are negative 5 and 3. Thank you so much, everybody, for listening in. I hope you have a fantastic rest of your day. Come to class with questions. Take care.